Look at the sensor array mounted on the roof of this car. It is navigating a busy city street entirely on its own. Systems like this are currently curating your social media feeds, filtering your emails, and mapping your commute. Once a technology becomes reliable enough for daily use, we usually stop calling it artificial intelligence. It becomes Google Maps or a Netflix recommendation. This shift in perception is known as the AI effect. This psychological quirk creates a gap in how we view the technology. While public discussion focuses on sentient robots or human-like chatbots, the actual work is happening in the quiet math running in the background. Technical definitions describe AI as a computational system executing tasks associated with human intelligence. These systems are built to maximize their chances of achieving a specific human-defined goal. The influence of these systems doesn't come from conscious thought. It comes from the continuous, invisible optimization of the data that shapes our daily lives. Early researchers tried to build intelligence by writing out step-by-step logic. They fed these handcrafted rules into mainframe computers, hoping the machine could reason its way through problems. This approach is known as symbolic AI. This method worked for high-level reasoning, like solving algebra, but computer scientists eventually hit a wall called Moravec's paradox. They realized that while algebra was easy to program, unconscious human instincts, like recognizing a face, were nearly impossible to code. To bypass that limit, the field moved toward machine learning. Instead of writing strict rules, engineers began feeding machines massive datasets, forcing the computers to discover their own statistical patterns. In supervised learning, humans label the training data with the correct answers. In unsupervised learning, the machine is handed a mountain of raw data and must identify structures and categories entirely on its own. By moving away from human-written rules and towards statistical guesses, computer science bypassed the previous barrier of hard-coded logic. This is an artificial neural network, the architecture behind deep learning. It borrows its structure from biology, passing data through input nodes and across weighted connections into multiple hidden layers before triggering an output. As the data moves deeper into the network, the layers refine it. The first layers might only detect simple edges. As those signals combine and pass upward, the higher layers assemble them into complex concepts, like a letter or a human face. Generative pre-trained transformers, or GPTs, apply this same logic to language. By mapping the semantic relationships between words, the network calculates the statistical probability of what the next token in a sentence should be. The math for this has existed for decades. What changed in the 2010s was the volume of data available on the internet, and a significant increase in processing power, driven by hardware like this graphics processing unit. This pairing of massive datasets and specialized hardware is what enables the current generation of tools. It is a process of brute force mathematics, executed by processors capable of crunching billions of probabilities every second. Because these models rely on millions of nonlinear guesses, they act as a black box. The designers themselves often cannot explain the exact steps the machine took to arrive at a specific decision. This lack of transparency creates risks when the models are used in the real world. If a system is trained on historical data, it will reproduce and amplify the human prejudices hidden within that data, leading to biased outcomes in areas like recruitment or healthcare. We see similar effects in social media. When algorithms are told to maximize user engagement, they quickly learn that polarizing content and misinformation keep people watching, creating filter bubbles that can undermine trust in public institutions. The energy needed to run these data centers is forcing tech companies to search for massive new power sources. They are now striking deals to restart reactors at sites like 3 Mile Island just to keep the servers running. These physical and social consequences demonstrate that these systems do not need a will of their own to be dangerous. A statistical engine simply executes its mathematical goals to their absolute conclusion, regardless of the side effects. This leads to the problem of alignment. As these models grow more complex, researchers are tasked with finding ways to ensure their optimization remains tethered to human welfare and safety.